The mode is the value that appears most often in a set of data. The mode of a discrete probability distribution is the value x at which its probability mass function takes its maximum value. In other words, it is the value that is most likely to be sampled. The mode of a continuous probability distribution is the value x at which its probability density function has its maximum value. So the mode is at the peak. Like the statistical mean and median, the mode is a way of expressing, in a single number, important information about a random variable or a population. The numerical value of the mode is the same as that of the mean and median in a normal distribution, and it may be very different in highly skewed distributions. The mode is not necessarily unique, since the probability mass function or probability density function may take the same maximum value at several points x1, x2, etc. The most extreme case occurs in uniform distributions, where all values occur equally frequently. When a probability density function has multiple local maxima, it is common to refer to all of the local maxima as modes of the distribution. Such a continuous distribution is called multimodal. In symmetric unimodal distributions, such as the normal distribution, the mean, median and mode all coincide. For samples, if it is known that they are drawn from a symmetric distribution, the sample mean can be used as an estimate of the population mode. Mode of a sample. The mode of a sample is the element that occurs most often in the collection. For example, the mode of the sample 1, 3, 6, 6, 6, 6, 7, 7, 12, 12, 17 is 6. Given the list of data 1, 1, 2, 4, 4, the mode is not unique. The data set may be said to be bimodal, while a set with more than two modes may be described as multimodal. For a sample from a continuous distribution, such as 0.935, 1.211, 2.430, 3.668, 3.874, the concept is unusable in its raw form, since no two values will be exactly the same, so each value will occur precisely once. In order to estimate the mode, the usual practice is to discretize the data by assigning frequency values to intervals of equal distance. As for making a histogram, effectively replacing the values by the midpoints of the intervals they are assigned to. The mode is then the value where the histogram reaches its peak. For small or middle-sized samples, the outcome of this procedure is sensitive to the choice of interval width if chosen too narrow or too wide. Typically, one should have a sizable fraction of the data concentrated in a relatively small number of intervals, while the fraction of the data falling outside these intervals is also sizable. An alternate approach is kernel density estimation, which essentially blurs point samples to produce a continuous estimate of the probability density function, which can provide an estimate of the mode. The following MATLAB code example computes the mode of a sample. X equals sort, indices equals find greater than 0%, indices where repeated values change, model, I equals max, % longest persistence length of repeated values, mode equals X. The algorithm requires as a first step to sort the sample in ascending order. It then computes the discrete derivative of the sorted list, and finds the indices where this derivative is positive. Next it computes the discrete derivative of this set of indices, locating the maximum of this derivative of indices, and finally evaluates the sorted sample at the point where that maximum occurs, which corresponds to the last member of the stretch of repeated values. Comparison of mean, median and mode. Unlike mean and median, the concept of mode also makes sense for nominal data. For example, taking a sample of Korean family names, one might find that Kim occurs more often than any other name. Then, Kim would be the mode of the sample. In any voting system where a plurality determines victory, a single modal value determines the victor, while a multimodal outcome would require some tie-breaking procedure to take place. Unlike median, the concept of mode makes sense for any random variable assuming values from a vector space. including the real numbers and the integers. For example, a distribution of points in the plane will typically have a mean and a mode, but the concept of median does not apply. The median makes sense when there is a linear order on the possible values. Generalizations of the concept of median to higher dimensional spaces are the geometric median and the center point. Uniqueness and definedness for the remainder. The assumption is that we have a real-valued random variable. For some probability distributions, the expected value may be infinite or undefined, but if defined, it is unique. The mean of a sample is always defined. The median is the value such that the fractions not exceeding it and not falling below it are each at least 1/2. It is not necessarily unique but never infinite or totally undefined. For a data sample, it is the halfway value when the list of values is ordered in increasing value, where usually for a list of even length the numerical average is taken of the two values closest to halfway. Finally, as said before, the mode is not necessarily unique. Certain pathological distributions have no defined mode at all. For a finite data sample, the mode is one of the values in the sample. Properties assuming definedness, and for simplicity uniqueness, the following are some of the most interesting properties. All three measures have the following property. If the random variable is subjected to the linear or affine transformation which replaces x by x plus b, so are the mean, median and mode. However, if there is an arbitrary monotonic transformation, only the median follows. For example, if x is replaced by exp, the median changes from m to exp but the mean and mode won't. Except for extremely small samples, the mode is insensitive to outliers. The median is also very robust in the presence of outliers, while the mean is rather sensitive. In continuous unimodal distributions, the median lies, as a rule of thumb, between the mean and the mode, about 1/3 of the way going from mean to mode. In a formula, median 3. This rule, due to Carl-Pearson, often applies to slightly non-symmetric distributions that resemble a normal distribution. But it is not always true, and in general the three statistics can appear in any order. For unimodal distributions, the mode is within standard deviations of the mean, and the root mean square deviation about the mode is between the standard deviation and twice the standard deviation. Example for a skewed distribution. An example of a skewed distribution is personal wealth. Few people are very rich, but among those some are extremely rich. However, many are rather poor. A well-known class of distributions that can be arbitrarily skewed is given by the log normal distribution. It is obtained by transforming a random variable x having a normal distribution into random variable y equals x. Then the logarithm of random variable y is normally distributed, hence the name. Taking the mean mu of x to be 0, the median of y will be 1, independent of the standard deviation sigma of x. This is so because x has a symmetric distribution, so its median is also 0. The transformation from x to y is monotonic, and so we find the median E0 equals 1 for y. When x has standard deviation sigma equals 0.25, the distribution of y is weakly skewed. Using formulas for the log normal distribution, we find, indeed, the median is about 1/3 on the way from mean to mode. When x has a larger standard deviation, sigma equals 1, the distribution of y is strongly skewed. Now here, Pearson's rule of thumb fails. Van ZWET condition. Van ZWET derived an inequality which provides sufficient conditions for this inequality to hold. The inequality mode median mean holds if f plus f1 for all x, where f1 half 0.7746 standard deviations of each other. In symbols, where is the absolute value. A similar relation holds between the median and the mode. They lie within 31/2 1.732 standard deviations of each other. Confidence interval for the mode with a single data point. It is a common but false belief that from a single observation x we cannot gain information about the variability in the population, and that Consequently, that finite-length confidence intervals for mean and/or variance are impossible even in principle. It is possible for an unknown unimodal distribution to estimate a confidence interval for the mode with a sample size of 1. This was first shown by Abbott and Rosenblatt and extended by Blackman and McColl. This confidence interval can be sharpened if the distribution can be assumed to be symmetrical. It is further possible to sharpen this interval if the distribution is normally distributed. Let the confidence interval be 1 alpha. Then the confidence intervals for the general, symmetric and normally distributed variates respectively are where x is the variate, theta is the mode and is the absolute value. These estimates are conservative. The confidence intervals for the mode at the 90% level given by these estimators are x plus or minus 19 x theta, x plus or minus 9 x theta, and x plus or minus 5.84 x theta for the general, symmetric and normally distributed variates respectively. The 95% confidence interval for a normally distributed variate is given by x plus or minus 10.7 x theta. It may be worth noting that the mean and the mode coincide if the variates are normally distributed. The 95% bound for a normally distributed variate has been improved and is now known to be x plus or minus 9.68 x theta. The bound for a 99% confidence interval is x plus or minus 48.39 x theta. Note McColl has shown that given a known density symmetrical about 0, that given a single sample value, that the 90% confidence intervals of population mean are where nu is the population median. If the precise form of the distribution is not known but it is known to be symmetrical about 0, then we have where x is the variate, mu is the population mean, and r and k are arbitrary real numbers. It is also possible to estimate a confidence interval for the standard deviation from a single observation if the distribution is symmetrical about 0. For a normal distribution with an unknown variance and a single data point, the 90%, 95% and 99% confidence intervals for the standard deviation are 0, 8, x, 0, 17, x, and 0, 70, x. These intervals may be shorted if the mean is known to be bounded by a multiple of the standard deviation. If the distribution is known to be normal, then it is possible to estimate a confidence interval for the mean and variance from a simple value. The 90% confidence intervals of the confidence intervals can be estimated for any chosen range. This method is not limited to the normal distribution but can be used with any known distribution. Statistical tests. These estimators have been used to create hypothesis tests for simple samples from normal or symmetrical unimodal distributions. Let the distribution have an assumed mean. The null hypothesis is that the assumed mean of the distribution lies within the confidence interval of the sample mean. The null hypothesis is accepted if where x is the value of the sample and k is a constant. The null hypothesis is rejected if the value of k depends on the choice of confidence interval and the nature of the assumed distribution. If the distribution is assumed or is known to be normal, then the values of k for the 50%, 66.6%, 75%, 80%, 90%, 95% and 99% confidence intervals are 0.50, 1.26, 1.80, 2.31, 4.79, 9.66 and 48.39 respectively. If the distribution is assumed or known to be unimodal and symmetrical but not normal, then the values of k for the 50%, 66.6%, 75%, 80%, 90%, 95% and 99% confidence intervals are 0.50, 1.87, 2.91, 3.94, 8.97, 18.99, 99.00 respectively. To see how this test works, we assume or know a priori that the population from which the sample is drawn has a mean of mu0 and that the population has A symmetrical unimodal distribution, a class that includes the normal distribution. We wish to know if the mean estimated from the sample is representative of the population at a pre-chosen level of confidence. Assume that the distribution is normal and let the confidence interval be 95%. Then k equals 9.66. Assuming that the sample is representative of the population, the sample mean will then lie within the range determined from the formula. If subsequent sampling shows that the sample mean lies outside these parameters, the sample mean is to be considered to differ significantly from the population mean. History. The term mode originates with Carl Pearson in 1895.